Hi there, this is Professor Shannon Gracey coming at you live from Miracosta College. Alright, it's getting to be pretty late, so bear with me here. We're covering sections 6.3 and from the Larson elementary linear algebra text. So here we go. First part deals with matrices for linear transformations, and let's see what we've got going on. So you can, read our goals there at your leisure. But let's go into talking about which format would be better. You've got, a transformation written as above, going from R3 to R3, and that's how your linear transformation is defined. Or you have the corresponding matrix version of the transformation. So what do you think? What might be better and why? Good. This is, I'm with this one, right? Because it's a lot easier to read, right? And easier to write for sure. And how do we enter everything in to MATLAB or Octave? Exactly, we enter it in as a matrix, so it's easier to adapt. To computer use. Awesome. Okay, so here we go. The key to representing a linear transformation as V maps to the vector space V maps to the vector space W by a matrix is to determine how it's going to act on a basis for V. So once you know the image of every vector in the basis, you can use the properties of linear transformations to determine this linear transformation of V for any vector V in the vector space V. So, do you remember what the standard base for Rn is? Come on, I know you can do it. Let's write it down. Write it in column vector notation. So, let's see what you've got. This guy is equal to the set of these column vectors. So the first one was great. It was 1, 0, 0, dot, 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 all the way down zeros. And then you'd go to your next one would be 0, good, 1, 0, dot, 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 0. And then as you go on in that manner, your last vector, where's that 1 going to be? Great, it's this last, in that last row. And it would start off all zeros until the component just before, and then you'd have the 1. Alright, so remember, this is going to be important. E1 is that first vector, E2 is that second vector, all the way down to En is the last one. So let's go ahead and label this. This is actually going to be important as we move on. Okay, so far? Great. Okay, so now we get to the standard matrix for a linear transformation. So as we have the linear transformation from Rn to Rm, we're going to let that be a linear transformation such that for our standard basis vectors EI of Rn, this is what we would get from our linear transformation. So you basically are going to get these coordinates. So if you have this going on in the linear transformation, then your m by n matrix, whose n columns correspond to these the transformations with the standard basis for Rn, you'll get this matrix. So T of V is going to equal to that standard matrix A times V for every single vector in Rn. Okay, so basically this matrix A, notice you get A times V. So V, remember, is the pre-image, and A times V would represent, the W vector we're usually talking about, which would be the image of the transformation. So A is called the standard matrix for T, and you're going to want to remember this guy, standard matrix for the linear transformation. All right, so let's just take a look at the proof of this. So what we have going on with the proof is, I know I technically started it down here, but I think space-wise we'll just go ahead and we'll start it just below the definition. By the way, if you're new to my videos, you can find this handout on www.mathchick.net, mathchick.net, and just look for the 6.3 to 6.4 handout, or once the guided notebook is up there, you would just search for the section in the notebook. All right, so let's check it out. So the proof. Okay, so let's think about what's V going to be. If we look at V, and just for space's sake, we're going to write it as a row vector and then transpose it to be a column vector, and it's going to consist of all of these elements, V1, V2, V3, all the way down to Vn, which is going to equal to, what do you think? Great, it's going to be a linear combination of the standard basis. So V1 times E1 plus V2 times E2 plus ... all the way down to Vn times En. So if I consider the linear transformation of V, so I'm basically looking at that linear transformation. Do you guys see it's going to be the linear transformation of all this stuff that we just said that V was? So V1 E1 plus V2 E2 plus ... plus Vn times the vector En. But properties of linear transformations allow us to do what? Good. The linear transformation is a linear operator, so you can apply it to each of these terms. All the way down to the nth term. And what are we allowed to do with constants when we've got a linear transformation? Awesome. You can bring them in front of the transformation. So T of V will end up being V1 times T of, oh sorry, I have a typo here. This should have been E1 right here. So times E1 plus V2 times E2, sorry, the transformation of E2, and then all the way down to Vn times this transformation here. Okay, so far? Great. So now let's take a look. So we're going to keep this guy on the back burner, okay? We'll come back to it soon, so remember him. Now what we're going to take a look at is we're going to take a look at what is A times V. So A times V, in general, remember we'd have A11, A12, dot, 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 down to A1N, and then A21, A22, dot, 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 all the way down to A2N. This guy is going to go, sorry, too close, all the way down to perfect A, M, and then 1. So you're in the mth row in the first column. This guy is going to go down to the mth row, second column, and then we'll end up having, as our last guy, we'll have A, M, N. Just a general matrix. And then your diagonal will go on as such. Actually, let's not, yeah. We're not calling it square though, so I'm thinking just to be on the safe side, we shouldn't do this. If it was a square matrix, it would be fine. We're going to leave it as this. Okay, so now V, as we said before, is a column vector, V1, V2, all the way down to Vn. So when we put that together, we're going to have, using matrix multiplication, do you see we'll have A11 times what? Perfect, V1, plus A, which way are we going? Perfect, 1, 2 times V2, all the way down to A, 1N times Vn. And then this guy is going to go A to 1, V1, all the way down to AM1 times V1. And you still have these sums. So you'll have A, I really should have done this first. You'd have the next term be A 2 V2 plus dot 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 plus A 2NVN. And then it would go in this manner until, I can do the second one here. So we'll do one more plus A M2 V2 plus dot dot dot, and we would end up with plus A M N V N. Good so far? Perfect. So let's think about what that is equivalent to. If we think about this guy, couldn't we write this as V1 times the column vector A11, A21 down to AM1? And then what would be next? You got it. V2 times A12, my bad, A12, A22, all the way down to AM2. And then continuing, we would have Vn times A1n, A2n, all the way down to AMN. All right?
Hi, Shannon.
Oh, sorry. My phone is actually talking to me even though it never actually works when I try voice commands. Crazy. Okay, So now let's take a look at what this is. So if you go back to if you look back at our definition, right? So T of E1 was A11, A21, all the way down to AM1. And T of E2, do you see all of these guys here? We have these down in what we've worked out. So if we go back here, we can say, hey, this is equivalent to V1 times T of E1 plus V2 times T, of E2 all the way down to Vn times T of En. And isn't that what we had up here? Do you see how it matches? So guess what? We're done. We can just, why don't we say a short statement on the side. In conclusion, T of V is equal to A times V for all of our vectors V in Rn. Isn't that awesome? So we're done with that one. You can check that bad boy off. Okay, so now let's see how we'd apply this. So we want to find the standard matrix for this linear transformation that's given. So here we go. What do we need to find? Good. Do you guys see that we're basically going to be, we have x's and y, we just have 2 entries here, right? Or actually no, we have 3 entries, right? So what we are doing, let's take a look at what we're going to find. We need to find our standard matrix for the linear transformation. So we start off by looking at T at 1, 0. So if I plug in, you know, a 1 for x, 1 for x in each of these parts. So, and then this time it would be a 0 for y. I would end up with 4 times 1 is 4, and then adding 0. So we would end up with, we'll put it in our column. Now we'll do it just as a row vector for right now. So we would end up with 4 in that first spot, and then 0. We always have a 0 in that second spot, and then in the third spot we would just end up with 2. Are we good? So T at 0, 1, and basically I'm saying that E1 is 1, 0, and I'm saying that E2 is 0, 1, right? And so this guy, again, we're going to be plugging in, you know, the same stuff, except for we've got a 1 for y this time and a 0 for x. So when we work that out, we're going to end up with, let's see, 1 right here, I believe, and then 0 again, and then -3. Are you guys good? Perfect. So what do we have? We do these in column format. So the standard matrix for T, drum roll please, is, we call it A, remember, and A is equal to these as column vectors. Because remember, we do A, this is like our A11, our A21, our A31. Let me get the little hand. So basically A11, this is, this 0 would be A21, A31, 3, 1 by definition. So here we go. We would have 4, 0, 2, and then 1, 0, negative 3. And that is the standard matrix for the linear transformation that was defined up here. All right? Okay, moving right along. Let's take a look at something, I don't know, a wee bit more complicated. So we'll have, we want to use the standard matrix for the linear transformation T to find the image of the vector V. So remember that the image of V is the output of your linear transformation. So we want to find that by finding our matrix A, which is the standard matrix for the linear transformation T, and then we'll multiply that to the vector V to get the image of V. All right, ready? Let's do it. So here we go. This time, let's see what we have. Do you see we have x's, we have 1, 2, 3, 4 I'm spacing out. We're in 4 space, right? We're in R4 right here. But do you see that these are all written in terms of x and y? So let's see what we have going on. Basically, oh, I'm sorry. I was looking at the wrong example. All right, no wonder it looked weird to me. So let's check it out. What we're doing is the standard basis for T of xy is going to have to be the same one we used last time. So E1 is going to be 1, 0, and E2 is going to be 0, 1. And that's because if you see the format here, you have your 2 coordinates x and y. But you're going to R4. So you're going to get, oh, why can't I ever think of the fancy name for that? I can always think of R5 as a quintuple. So anyway, a 4-tuple. So let's do it. What we have here is figuring out each of our things. So T evaluated at E1 is equal to T at, or the linear transformation with the standard standard basis is going to be T at 1, 0, which is going to be perfect. 1 plus 0 is 1. 1 minus 0 is 1. 2 times 1 is 2. And 2 times 0 is 0. Okay, so far? All right. T at E2 is this transformation here. So then we're going to have, they're swapped now, so we will have still 1. X minus y will end up being negative 1. 2 times 0 is 0, and 2 times 1 is 2. Okay, so far? So what we found from that information is that A, this gives us that A is equal to, remember they're column vectors, so 1, 1, 2, 0, and 1, negative 1, 0, 2. Good so far? Perfect. So now what's left? You got it. We need to consider our vector V, which was 3, negative 3. It's right up there. And our vector A is written to the right up there. So we just need to find A times V. So we'll have our A, which was 1, 1, 1, negative 1, 2, 0, and 0, 2. And our vector V is 3, negative 3. And so if you look, we have a 4 rows by 2 column vector A multiplying a 2 by 1. So we will end up with a 4 by 1. And You can either do the multiplication in your head, or we can do it on Octave. It's going to be pretty easy though. We'll have 1 times 3 plus 1 times negative 3 is 0. 1 times 3 plus negative 1 times negative 3 is going to be 3 plus 3, right, which is 6. And then 2 times 3 is 6, plus 0 times negative 3, and then 0 times 3 is 0, and 2 times negative 3 is negative 6. So what did we find? We found that the image of 3, 3 under this linear transformation is the vector 0, 6, 6, negative 6. Are we good? Awesome. So just to recap, we were being asked to use the standard matrix, okay, for that linear transformation, and we needed to find the image of the vector v. So basically the output of the linear transformation. So we first found A by evaluating our linear transformation at the standard bases, and then we multiplied that resulting matrix by the given vector v, and we found the image of 3, 3 under this linear transformation to be 0, 6, 6, negative 6. All right? Okay, so here we go. Moving right along. So now example 3, let's see what we've got. We've been given that t is the reflection through the yz coordinate plane in R3. So basically, t at x, y, and z is equivalent to the opposite of x, or negative x, y, and z. And then we're given v as a vector in R3, 2, 3, 4. So we need to find the standard matrix for this transformation. So what do? Good. We need to find t at E1, which is going to be, in this case, t evaluated at, perfect, 1, 0, 0, sorry, which is equal to, good, negative 1, 0, 0. So I'm plugging that into these guys. All right, what about t at E2? Good, that'll be t at 0, 1, 0, which is, let's see, we'll get 0, we'll get 1, and then we'll get 0. And then t at E3 is going to be t at 0, 0, 1, which is 0, 0, 1. Are we good? Perfect. So now our standard matrix A is remember, we write those as column vectors, so negative 1, 0, 0, 0, 1, 0, and then 0, 0, 1. Are we good? And what is that matrix called? It's a special kind of matrix. You got it. It's a diagonal matrix. We'll be talking about those a little bit in 6.4. Alrighty, so use A to find the image of the vector v, the image of the vector v. So remember, we want the image of the vector v under the linear transformation. So how do we find that? Perfect. We need to do A times v. So A, remember, was this diagonal matrix here. So we have negative 1, 1, and 1 in the diagonal. And then our vector v, if you come up here, is just 2, 3, and 4. And when we multiply that one, again, that's an easy computation. We start off with a 3 by 3 times a 3 by 1, so we'll get a, awesome, we'll get a 3 by 1. So we're going to get, GC will just get negative 2, because negative 1 and then times 2 is negative 2, and then zeros the rest of the way. And then this guy is going to be 3, and this guy will be 4. Are we good? Perfect. And let's see, we found it here. So, or if you want, you could write it as, let's do this. So t of 2, 3, and 4 we found to be negative 2, 3, 4. So we'll circle that. So now if we sketch the graph of V and its image. So it's been a little while since I did 3D graphing, so let's check it out. If we have each of those boxes be 1 unit, we're going to have to go up a little for V. So that'd be like 1, 2, 3, 4. Going up the Z rather, not V, the Z. And basically, remember V was 2, 3, 4. And I'll do this guy in blue. T of V was equal to negative 2, 3, 4 from our results above. So, graphing our, doing the picture of our first one, the V. So we're going to go, if on the XY plane you'd have this ordered pair, right? So that's 2 and then 3. And then we have to go up to, what was it, 4. So we'll basically be following, we're up to 4. So we basically have kind of a big 3D shape, right? So you have like this guy, and then we got to go make sure we stay straight, and we're going parallel with this axis, but it's going to go down a little, right? So 0 would be here, 1 would be here, 2 would be here, 3 and 4. So we got to go up here and then over, and we would get 2, 3, 4. Would that be there? Let's see how that works. So we should have I think that's all right. So our 2, 3, 4 would be here, and it would be coming up from here. Okay, so this is our vector V equal to 2, 3, and 4. This is probably a little off. I should have come up a little bit more like this. Let's fix it a little. Hopefully I won't erase the whole thing. So let's fix this line a little bit. Jonathan's going to be laughing at me because I was doing the same thing in class. There, I think that's a little bit better. So it's about here. Okay, so that's our V. And that's all crooked. Oh my goodness. Someday I'll get to leave work. That's our V. Okay, and then our transformation, under V under T, our image of that, of the linear transformation is negative 2, 3, 4. So we'd go back on the X here. We'd still be out here, 1, 2, 3, right? And then we'd be going over from here, right? Because remember that was our 4. And then this is going to be going straight up here. That's not so bad, I don't think. So then this guy is going to be, well, not curved. And actually we shouldn't have a dot there, so we'd have, you get the picture. So this would be our vector -2, 3, 4, which is the image of the linear transformation. Okay? All right, nice. So, moving right along, now let's talk a little bit about composition of linear transformations. So just to give you a heads up, this was supposed to connect. So here, let's just figure out what we've got. So let's say that this guy right here, this space is Rn. Okay? And this right here is a vector v that is part of Rn. Now, this first linear transformation, call it T1, is mapping to this vector v. So you have the image under this first linear transformation is the vector w. All right? Now, the vector w is being transformed as well. Call it linear transformation 2. And it's transforming to call it some, oh, and by the way, what space would vector w be in? Vector w would be in Rm. Now, if we go to Rp, okay, then this vector here would be vector u. And hey, let's say we want to go directly, right? So if you think about it directly, you've got running out of colors here. If you think about it directly, this is just our general linear transformation T, all right? And what we've just illustrated here is that T of V is actually T2 composed with T1. So you've got this whole thing T is equal to, so we have our T2, and then the operation is we're going to have the composite, and then it's composed with T1, which by definition is going to give us T would equal to T2 evaluated at T1, and what would be in T1 V good. Okay, so far? So, and let's be nicer about this notation. So we'll call this guy T at V. Alrighty, so let's take a look at what we have going on. So we have got this theorem here, composition of linear transformations. So you can read through that. You know, the conditions are that T1 and T2, T1 goes from Rn to Rm, and T2 goes from Rm to Rp, are linear transformations. And they have standard matrices A1 and A2 respectively. So the composition of T going from Rn to Rp, which is defined as we defined above, is a linear transformation. And guess what? This is awesome. The standard matrix A for T turns out to be given by the matrix product A2 times A1. So let's check out the proof. So with this guy, we would let u and v. So let's think about this. So first of all, remember that instead of doing all 10 axioms to see if something is a vector space, it's nice to do what? Good. If you can state that your set is non-empty and a subset of the linear transformation, then you're set. So if you look at this, do you see that each of these separate linear transformations are subsets of T? So we shall state that, right? So we're going to let u and v be vectors in Rn, and we're going to let C be a scalar, and we're going to note that, what do we need to note? We need to note that the parts of the composition are, so T1 and T2 are non-empty subsets of T. So since we said that we've got non-empty subsets of T, what do we have to show? We just need to show, perfect, closure under vector addition and closure under scalar multiplication. So here we go. First one, we'll do the addition. So remember, it has to be in general if you think it's going to work. So T of the sum of these vectors, u and v, is going to equal to, by definition, all right, T2 that's evaluated at T1 at u plus v. But T1 and T2 are linear transformations, right? So this is going to be equivalent to T2 evaluated at T1 at u plus T1 at v. Now, what will we get with this one? We would end up getting T2 evaluated at, or actually not evaluated at, T2 times no, T2, my bad, I'm sorry, I'm tired tonight. So T2 at T1 of u plus T2 at T1 at v. Okay, so far? But what is that? Good, that's just going to be capital T at u plus capital T at v, which shows closure under, good. This shows, so it's closed under vector addition. Okay, so now C is any scalar. So basically with this guy we need to show that T at C times u, we'll just use u, and we need to see what we get for this guy. So this would be T2 at, I don't like the brackets. I'm not going to use the brackets. I think it makes it more confusing. It doesn't look as linear transformation-ish. And so we would get these guys. Maybe that'll make it look more apparent. Alright, so then we'd get T2 evaluated at T of what? T1 of C times U. And what is that equal to? Good, we can move the C out to in front of that T1. And we're close, right? Because we have to get it in terms of that composition. So we need the C to move out even further. So we'll have C times T2 evaluated at T1 at U. But what is this? Good, it's C times T at U. So it's closed under scalar multiplication. So what do we have going on? That means that actually we need to show one more thing. Okay, so this part, the moreover, the standard matrix, this guy here for T is given by the product. So we got to prove that guy. So it should be fine. I'm going to just do this as number 3, that moreover statement. So T at V is equal to T2 rather at T1 at V. But what is this equal to? What is T1 at V in terms of matrices? Perfect. That is going to be A1 times V, right? And so we'll end up with T2 of this product. And what can we do with this guy? So we'll have, perfect, we'll end up having A2, okay, at A1 at V, which is going to give us, good, we're going to end up getting A2 times A1 times V. So this is showing us that I'm going to go to the next page. This shows that A2 times A1, which is equal to the happy A for our standard matrix, is the standard matrix for the composition. And that's all we had to show. All right, so we're all done with that proof. So now let's check out a problem. Okay, so example 4, we need to find the standard matrices A and A prime for these two compositions. So let's check it out. We've got, for part A, no, it's not part A. So for the first composition, this is what we'll have. So first off, let's figure out what we're going to have. We'll do it on the side here, do some side work. So do you see that T1 at E1 is going to be equal to, so what's our first linear transformation? That would be doing T1 at 1, 0, which is going to be perfect. It's going to be 1, 0, 0. Good so far? And then T1 at E2 is going to be T1 at 0, 1, which is good. 0, 1, 1. Now T2 at E1 is T2 at, what's our good? It's going to be, we've got 3 of them, right? At 1, 0, 0, 3 coordinates. And what do we get? We'll get, it comes out as y comma z. So this one will just be 0, 0. Good so far? And then we'll have T2 at E2 is going to be T2 at 0, 1, 0, which will give us 1, 0. And then T2 at E3 will be T2 at 0, 0, 1, which is 0, 1. All right? So that gives us the information we need for A1 and A2. So based on that, A1 is going to be what? What do you think? Standard matrix. Good. It's going to be the column vectors, right? That we had found. So what we'll have is we'll have this one had 1, 0, 0, and then 0, 1, 1. Are we good? And then A2 is going to be good. It's going to be, this time it's going to be, actually, yes, we'll have 0, 0, 1, 0, and 0, 1. And now let's look at these compositions. So that's our setup work. So T is equal to, if we do the first one, T2 composed with T1, that's going to be T2 evaluated at T1 of V. But what do we know? That that's just going to be what? We learned that, let me go across. We learned that this is A2 times A1. Are we good? So we'll have A2, 0, 1, 0, 0, 0, 1 going across times A1. So we have a 2 by 3 multiplied by a 3 by 2. We're going to get out a, good, a 2 by a 2. And then we'll end up with, so 0 times 1, 1 times 0, 0 times 0. I think we'll get 0 for the first component. Now, 0 times 0, 1 times 1, 0 times 1. We just get a 1. Sorry, it's too close. And then going down, 0 times 1, 0 times 0, 1 times 0, we'll get another 0. And then 0 times 0, 0 times 1, and 1 times 1, we'll get 1. All right? And so that is our answer for the first one. All right? So this is this guy. Now, the second guy is looking at it from the other way. So if we do T1 composed with T2, remember that's T1 at T2 at V. But what we know is that's going to be equal to, good, A1 times A2. Perfect. So we will get A1 was this guy. A2 is, so we have a 3 by 2 multiplied to a 2 by 3. So what are we going to get out? Good, a 3 by 3. All right, so again, doing it real quick. Remember, it's first row time, the first row times first column. So 1 times 0 plus 0 times 0 is 0. And then to get the component to the right, we'll be doing 0. We'll be doing, 1 times 1 plus 0 times 0 is 1. And then to get the third one over, we'll have 1 times 0, 0 times 1 is 0. So going along a little quicker, we're going to end up with 0 here as well, 0 and then 1 for the second row, and then the third row will be again 0, 0, 1. Good so far? Okay, perfect. So this is the answer to this guy, and we are all done with that problem. Okay. So here we go, definition of inverse linear transformation. So if we have this situation, notice that you're going, instead of Rn to Rm, both of these are going from Rn to Rn. So if that's true, and every V in R has this result, every V in Rn rather, has the result where when you evaluate T2 at T1, the first linear transformation, you get V. And if you go the other way and you still get V, what do you think they'll be? Good. Then T2 is called the inverse of T1. And T1 is said to be invertible. Now, it's good to note that not every linear transformation has an inverse. So if T1 is invertible, though, then the inverse is unique. So that's important. And it's going to be denoted by T1 inverse. Okay, so next on the list is Theorem 6.12, which gives us conditions, equivalent conditions. So it turns out that if you have, a linear transformation going from the same to the going from Rn to Rn, and it has a standard matrix A, then it turns out that T is invertible. T is an isomorphism. So what did that mean again? Good, an isomorphism meant that it was both one-to-one and onto. So remember that you find out if T is one-to-one by seeing if the kernel just had the 0 vector and that's all. If that's true, then it's one-to-one. What about onto? Onto means that every image has exactly one pre-image. Good. So we'll also have that A, it turns out to be invertible. Alright, so if T is invertible with standard matrix A, then the standard matrix for T inverse is going to be A inverse. So that's pretty groovy. So let's look at the proof. So we'll do how 1 implies 2, and then how 2 implies 1. This is the game plan. And then we'll do the last condition. Then we'll do the last thing. All right, to show that 2 and 3 are equivalent. And then finally, we will do the last statement. So here we go. So this guy, 1 implies 2. that means that our supposition will be that T is invertible, and we need to show that if that's true, then T is an isomorphism, which means we have to show that T is good, one-to-one and onto. So here we go. We're going to let T be invertible. So that means if we have T of V1 equal to, and that's a vector V1, equal to T of V2, then what would be true? That implies that, good, T inverse of this transformation is equal to T inverse of T2, T of V2. So, but what if T is invertible, then that means that what has to be true? We would end up getting that V1 has to equal to V2, because if it's invertible, you get what's inside. I missed a parenthesis here. Okay, so that tells us that T is one-to-one. It's another way of showing one-to-one. Okay, now T is onto. We have to show that T is onto. So let's look at the game plan. So if you consider some wvector W, for any vector W that's an element of Rn, T inverse at W, okay, has to be what? What did we say about this? In order for it to be onto, you know, every image has to have one pre-image. So isn't it true that we just showed that T was one-to-one by saying that if you have, if two linear transformations of different vectors equal each other, then the vectors have to equal each other. So therefore, if you evaluate the inverse at W, it's got to be a vector V. So that shows that it's onto, and we finished that guy. Next up, we have 2 implies 1. So let's see what we're doing. Now our supposition is that let T be an isomorphism. So that means that T is one-to-one and onto. So let's define T inverse as follows. So here we go. So since T is onto, all vectors W that are elements of Rn, so actually for all vectors W that are in, I'll squeeze that in here, that are in Rn, there exists a V that belongs to Rn such that T at V is W. So, because T is 1 to 1, what does that mean? Remember that one little fact? If it had an inverse, the inverse was good. The inverse was unique, right? So V has to be unique. So T inverse would be T inverse at W equal to V if and only if if and only if what? Good. If and only if T at V is W. So, lastly, let's consider the last little piece of that puzzle is that finally the corollaries. So back in I think it was what 6.2 or something, or 6.1, the corollaries to theorems 6.3 and 4 show that show that 2 and 3 are equivalent. So properties 2 and 3 are equivalent. Alright, so we finished that guy up. Now the last one we need to do is that third one. So if T is invertible, so remember this was our statement. If T is invertible with standard matrix A, that's what our supposition is. So let's start with if T is invertible, what do we know is true? T of x equal to A times x implies that T inverse at T at x is good. X and that is going to, I'll just write it out, which equals, yeah, just sloppy. I'll go to the next line. Which equals A inverse times AX, because remember that if T is invertible, then T inverse is A inverse. That's where I'm getting that. So the standard matrix of T inverse is going to be A inverse. Actually, that's what we were showing, right? Yes, perfect. So, done with that whole proof. That was a long one. So now, here we go. We're going to have our fifth example. So we want to determine whether the linear transformation is invertible, and if it is, find its inverse. So here we go. Again, don't forget about this stuff. T at E1 is T at perfect 1, 0, which is going to be 1, 1. And T at E2 is T at 0, 1, which is going to be 1, negative 1. So therefore, A will be, using those as column vectors, 1, 1, 1, negative 1. And do you remember how to figure out if it's invertible? Good. If the determinant of A is non-zero, then it's invertible. So remember, determinant of A will be 1 times negative 1 minus 1 times 1. And what is that? I think we get negative 2, which is not equal to 0. So T is invertible. So now let's find the inverse. So do you remember that A inverse, if you have a 2 by 2, is equivalent to 1 over the determinant, which we found to be, good, negative 2, and then times, you flip the diagonals, okay, so A11 and A22, and then you put the opposite sign in front of the other two. And so we will get, at the end of the day, positive a half, positive a half, positive a half, and then negative a half. And we're done. All right, so now actually we want to know what exactly the linear transformation would be, right? So T inverse, therefore, at X and Y is going to be, so you got to think about your original transformation, right? So the first one was X plus Y, so now we're going to be doing, we have 1/2 X plus 1/2 Y, again going down, comma, 1/2 X minus actually it's minus a negative, right? 1/2 Y. So that would give us 1/2 X plus 1/2 Y. And then 1/2 X plus 1/2 Y. Kind of cool. All right, so that's what we were looking for. All right, so now it gets a little crazy. Let's look at our transformation matrix for non-standard bases. So basically, this is the linear transformation of V1 with relative to B prime, and you're still going to get, you know, your A11, A21, etc. So there'll be column matrices or column vectors. So it turns out if you've got this true, then the m by n matrix whose n columns correspond to T V1 of B prime is going to be this. And again, I don't think we should have had these dots, so let me take those out. So that's going to be such that T at V relative to B prime is equal to A times V relative to B prime, to B, my bad, to B. All right, and that's for every V in the vector space V. So let's figure this out. So we want to find T at V by using first off the standard matrix and second off the matrix relative to B and B prime. Basically T at 1, 0, 0, because you're going from R3 to R2, is going to equal to 1 minus 0 is 1, 0 minus 0 is 0. T at 0, 1, 0 is? Good, we'll have negative 1 and 1, and then T at 0, 0, 1 will give us 0 and negative 1. Okay, so far? So what does that tell us? That tells us that A prime, so we'll list it over here, is equal to this matrix here. So this is the standard matrix for this particular linear transformation. Okay, so far? Awesome. So now we're being called on to find what exactly is this linear transformation, right? So how would we find that? Good. T at V is going to be A prime times V, which will be 1, 0, negative 1, 1, 0, negative 1. And then what was our V? It was 1, 2, 3. So we have a 2 by 3 matrix being multiplied by a 3 by 1. So we're going to end up with a 2 by 1. So 1 times 1 plus negative 1 times 2 plus 0 times 3 will give us negative 1. And 0 times 1 plus 1 times 2 plus negative 1 times 3 gives us another negative 1. So that's the first answer. Okay. So now what we have found is that we found basically that T at 1, 2, 3 is equal to negative 1, negative 1. All right. Part B. So now we need to find the matrix A. So T at 1, 1, 1 is going to equal to what? Good. It's going to be 1 minus 1 is 0 and 1 minus 1 is 0. T at 1, 1, 0 is going to be again 0 and then 1. And T at 0, 1, 1 is going to be negative 1, 0. So now let's think about this, because what we need to do is in order to get A, we're going to need to write this as a linear combination. So we need to look at the vectors in B prime. So we have 1 and 2, and we have 1 and 1. And we need to write the vector 0, 0 as a linear combination of these vectors. All right. So that's the coordinates will give us the numbers we need for the matrix A, the standard matrix A. So let's do it. Basically, this one's kind of easy, right? If we just do 0 plus 0, we'll get 0, 0. Do you see that? So that one wasn't so bad. Now this guy, again, we got to use 1, 2, and 1, 1. So let's see if we can just eyeball this and get our combination. So let's see, we need to get 0, 1. So gosh, if we just subtract them, I think it'll work out fine. So do you see we'd have 1 times that minus 1 times that one? Good so far? Awesome. So lastly, we got negative 1, 0 here. We need to write that as a linear combination of these guys. So let's see. I think if we kept the first one the same and then we subtracted 2 times the other one. Let's see if that works. 1 minus 2 is -1, and 2 minus 2 is 0. So looking at making column vectors basically out of the red coefficients that we did, this is what we're going to have. So A will equal 2. So 0, 0, making that a column vector, 1, -1, and then 1, -2. Okay, so far? Awesome. So now our next job is we need to equate the vector 1, 2, 3, and then this time it's going to be harder, so we'll say C1 times 1, 1, 1 plus C2 times 1, 1, 0, and then plus C3 times 0, 1, 1. So now what we've got going on is we can have this way that we can calculate it. So this one will end up making the matrix 1, 1, 1. Going down in columns, I'm starting with the C1. 1, 1, 0, and 0, 1, 1. If you need to see it better, you could multiply out, the C1s and C2s and the C1, C2, and C3 and see the system of equations you come up with. And actually, we need to put down the 1, 2, 3 so we can find out what the vector V relative to B is. So it turns out when you row reduce this bad boy, what happens is you get this matrix. So you get your identity matrix, and you get 2, -1, 1. So what we found is this. From that solution, we found that the vector V relative to the basis B is equal to, so we basically just wrote V as a linear combination of our basis B, and that's equal to 2, -1, 1. Okay, so far? Awesome. We would just multiply, so T of V relative to B prime is just going to be 8 A times V relative to B, and that's going to give us our A vector, which remember up here was 0, 1, 1, and then 0, -1, -2 going across. And then we just found that second vector to be 2, -1, 1. And when we complete that product, let's see, 0, -1 plus 1, we'll get, so what's that going to be? A 2 by 1, right? So we'll get, what was that, 0? And then 0 times 2 plus -1 times -1. So we'll get 1 minus 2 there, which will be -1. So that's our result for this guy. So here we go. So if you want to write that out, we can say that T of V is equal to, looking at our solution here, 0 times 1, 2 minus 1 times 1, 1, and look what we get. We get -1, -1. And isn't that what we got up here? Oops. T of 1, 2, 3 is -1, -1. Actually, let me write it in that format. Okay, so T of 1, 2, 3 was equal to this guy. So two different ways to find the, the same result. So moving along, let's take a look at this example. So one thing that we want to note, so basically the transformation is going to be the derivative of these guys. So our set W, our set B is a basis for a subspace of W, which is this of the space of the continuous functions. All right. So, and dx is the differential operator on W. So let's figure this out. First of all, what you have here is, if you look at the first one, this is like e to the 2x plus 0xe to the 2x plus 0x squared e to the 2x, right, for our first one. And xe to the 2x is equal to 0 of these e to the 2x's plus one of those xe to the 2x's, and then we've got 0 of this guy. And then x squared e to the 2x is equal to, the first guy is 0 out, and then you're left with one of these x squared e to the 2x's. Okay, so far? Awesome. So now, let's take a look. So what this will bring us to is that if we do this differential operator on e to the 2x, right, what we will have is the other ones will be 0, and this derivative is good, 2 e to the 2x. Now what about this guy? So we're doing our transformation of our xe to the 2x. The other, the first and third term 0 out, and the derivative, remember there's a product rule, so we'll have x. Actually, I'll do this one. I'll differentiate x first, and we get 1 e to the 2x plus 2x e to the 2x when I clean it up. And then thirdly, we will have the first and second term zeroed out, and we'll end up with 2x e to the 2x plus x, we'll end up, do you see, with 2x squared e to the 2x after differentiating. Good so far? So now what we look at is we look at what we have in each area. So we look at the ones where we have an e to the 2x, right? And the one down here has 0 of them. Then we look where we have a 2x e to the 2x, and then we're going to look where we have the 2x squared e to the 2x. So basically our matrix under the transformation, oops. So our matrix under the transformation relative to B is going to be A, good, which is, so now we basically, if we kind of fill this in, we have plus 0x e to the 2x plus 0x squared e to the 2x. This guy is going to be what? We have 1 e to the 2x plus 2x e to the 2x plus 0 of these x squared e to the 2x's. And then over here, if I was going to kind of squeeze one in, we would end up having 0 e to the 2x's plus the other one. So let's check out that this trend, and let's check out what we have. So if you look here, we'll have, if we think of the e to the 2x's, and we go across, we'll have 2, 1, 0. So I'm looking at 2, 1, 0. 2, 1, 0. So then, taking the next guy, all right, let's see what we have. We end up having 0, 2, and 2. So again, we'll go across and we'll have our 0, our 2, and our 2. And then lastly, do you see how we have 0, 0, and 2? So going across, we'll have 0, 0, 2. And that's how we get our standard matrix A. So what you have is this first row, if you will, is kind of like the e to the 2x row. The second row is your x e to the 2x row. And then the third row is your x squared e to the 2x row. So you end up having, that's why you end up getting the matrix that you do. All right? So that guy's done. And so that finishes up the lecture on 6.3. Have a great night. Bye.